Good morning, class. I am Abba Enoch, Chief Technologist in Physics Department. I'll be taking you Physics 127, Experimental Physics 2. Let me give a background to what we are to do. The manual you have in your hand is designed to give students practical application of the theories in optics and electricity. From Physics 117, you have done degree of mechanics and waves in the first semester, and we hope that in this work you appreciate a lot from what the practical knowledge of optics is, and you apply it to confirm what you have learned in your theory class. You know, in your Physics 117, you were told that there are key things you observe when you do get to the lab. Principally observation, handling of instrument, reporting of your particles, and then graph plotting. Of course, you also take necessary precautions. Having that at the back of your mind, that no experiment is error-proof, but how well you handle your experiment and how you try to observe necessary precaution go a long way on how your results will come out true or otherwise. We'll go straight to one or two experiments we'll do in this course, and then of course, you know most of the work, you can't do them off the lab, so a bulk of the work will be done when you come to the lab to handle the apparatus yourself. We're looking at experiment 1, which is determination of focal length of a convex lens. The apparatus you require for this work are 1, a ray box, an optical bench, a convex lens, something like this, convex lens, the lens holder, and the screen. The setup is as shown in the diagram on the slide. This is your ray box, this is your convex lens on the lens holder, and of course the capital S there is the screen showing the image that is displayed from the object distance there. The procedure is you measure the rough focal length of the convex lens. The rough focal length, it is called rough because it is not the exact focal length of this lens. How do we measure it? We so do by focusing a distant object, maybe a pole or the wall of the building where you have a reflection of light from the window. If you do varied like that, you will see where the image of the ray of light coming from the window is sharp on the wall, and with your hand held to that point where the image of the ray of light coming from the window is casted, you measure that distance with a meter rule. That gives you the rough focal length of this lens. What are we to do with it? In this work, you are not told where to measure the object distance, as it were, on the optical bench, but you impute the raw focal length that you have measured by focusing on a distant object into the relation provided in this slide, which is 1.5f is less than u is less than 4f. What is that showing us? Assuming, for instance, our raw focal length is 10. If you put 10 in place of 10 cm, if you put 10 cm in this relation, 1.5f is less than u is less than 4f, you will realize that you have 15f is less than u is less than 40f. The interpretation of that is your initial u should be greater than 1.5f, which is 15 in this case now, and the last object distance should be less than 4f, which is 40 in this case now. When that is done, we can now go to the optical bench and then measure or determine where our first u, which is the distance of the ray box from where the lens holder and of course the lens is placed, which will now give us an image on the screen. Because we are required to have 5 different points, we will choose our first u so that since our 1.5f here is 15, it means that my first u can be 16, can be 18, it can be 19. But I should choose my first u so that the 4 remaining intervals of u that I will choose will be such that it will not be equal to 4f or greater than 4f, which is 40 in this case. Well, if I choose my initial u to be 16, if I choose 4 interval, maybe the next one, second u will be 20, the third one will be 24, the other one will be 28, and then 32. I'm less than 40 and I'm greater than 15, which is my 1.5f, so I am good to go. I can also choose 17, of course, or remain at 16 and still maintain or interval of 5, which will give me the next one will be 21, 26, 31, and then 36. I can choose 17 or 18, but ultimately, at the end of the day, I am following the rule that say, or the relation that say 1.5f is less than u, and at my final u, I am less than 4f, which is 40. When that is done, I vary my screen to get a sharp image on the screen, and of course I will measure the interval between the lens and the screen, and then I will have image distance measured from the work I am doing, and I get to the questions that are provided for me in this work. Question A, plot a graph of 1 over u. Of course, you know that your u here is your object distance and your v is image distance. Don't mix it with your u and v in mechanics. In mechanics, your u is your initial velocity, your v is final velocity. In optics, your u is your object distance and your v is your image distance. Be clear about that and be sure of how you handle this value. So the questions provided for us here, question A, we plot a graph of 1 over v against 1 over u and measure the intercepts C1 and C2 on both axes, and then you evaluate C is equal to C1 plus C2 all over 2. B, plot a graph of V over U against V and measure the slope, and of course we follow through as it is in this line. Thank you. The second work we are doing here is called linear magnification. Like you were told, again, you know the rule. You gave us the title of the work, the number of experiment, the date of the experiment, like you know in Physics 117, and of course, the apparatus listed out on the line for you, and then the procedure, which is the step-to-step approach you will take to get the work done. And then you draw this as it is on this slide. You are provided here with the ray box. You are provided also with a lens holder and a lens, and of course the screen. This is your ray box. This is your lens holder and the lens, and then this is your S. Here, we are interested in that opening, that aperture in the ray box, where the ray of light will be coming from. With your meter rule, you measure the opening, that small opening, where the light is coming from, the ray of light is coming from, and you keep it all through the experiment as your object. Now, when that is done, you measure the interval between where the ray box is and where your lens holder will be placed on the optical bench. The interval, the first one, is given as 25 or 20, sorry, 20. So that is the interval between the ray box and the lens holder. When that is done and kept in place, you vary your screen to where you are going to have a sharp image of that image, that circular image of the object on the screen. Where you have the sharpest object is where your Y will be. You know, here we are talking about object distance and image distance, but we are using the interval between the X and the Y to get our image distance on the screen. The image we are talking about here is not the X and the Y, but we are using the X and the Y to get a sharp image of the object on the screen, which is now denoted as our capital S. The object distance is our small s. Of course, when that is done, you get your image, your capital S on the screen. You shift to the next X, which is now 25. You vary your screen to get a new value of Y, and of course measure the image distance, image of the opening of the ray box now, which is noted with your capital S on the screen. You do that for 30, 35, and 40 respectively, and you are done with this work, and you are also required to determine your capital S, which is measured with the help of a meter rule, of course, where you have the sharp image on the screen is your Y, and then you determine M. What is M in this case? M is magnification, and magnification is a ratio of the image distance over the object distance, which in this case is represented with our small letter s, the opening on the ray box, and of course the opening again as the image is on the screen. When that is done, we answer the questions that we are asked. Question A is to plot the graph of M against Y and determine the slope of the graph. You state 2 precautions and you've taken to ensure accurate results. You are given also that M is equals to C plus Y over K. Use the graph to determine K. Find the value of Y. When M is equals to 0, you plot the graph of Y, 1 over X against 1 over Y. Given that 1 over X is equals to A over Y plus 1 over K, where A and K are constant, we use the graph to determine the value of A and K. You know, as it is a practical course, you cannot do more. It can't be done in abstract. So you appreciate the reality of the work when you come to the lab and you put your hand on the apparatus to seeing what we have explained on this slide, and you appreciate that what we are saying is practicable and it can be done, and then you will be assessed based on how good or otherwise your work is done. Thank you. Enjoy your time in the lab as you continue to do your work, and I pray for all the best for you in your course of study in this institution. Thank you.